Hello viewers, welcome to this next lecture on this MOOC course on mathematical portfolio theory. You would recall that so far we have been looking at the mean variance framework due to Markowitz, and we have looked at optimization of portfolio in terms of minimizing the variance as an indicator of risk, and then we looked at what is an opportunity set and the efficient frontier. And we made an important statement that any portfolio on the efficient frontier can be obtained as a combination of two portfolios on the efficient frontier. And I looked at the case when the portfolio comprised of only risky assets, and then we extended this to the case when a portfolio comprised of a risk-free asset in addition to a collection of risky assets. And in the last class we have talked about something which is known as the capital market line. So, in this class we will go ahead and talk a little bit more in that framework, and in particular we will look at what is known as the capital asset pricing model, and we will talk about what is known as the single index model, which is sort of an alternative way of modeling the return of a particular asset or a portfolio in terms of the market portfolio. So, accordingly we begin our lecture with a discussion on the capital asset pricing model or CAPM. Alright, so let us begin with a brief motivation of the capital asset pricing model. So, we can say that the detailed investigation after the development of the Markowitz model. So, Markowitz model turned out to be a very important milestone in financial engineering. So, obviously, there was a lot of work that was done after the Markowitz model was presented. So, this detailed investigation that were a follow up to the establishment of the Markowitz model, this resulted in the capital asset pricing model, which is commonly known in the parlance of finance as CAPM, and which is sometimes referred to as what is known as the security market line or SML. Okay, now this framework of CAPM is based on certain elaborate list of assumptions, and we will enumerate them one by one. So, the first assumption is that investors in capital assets, that is all terminal wealth producing assets, that means you make an initial investment and you basically then receive a final amount of payment. So, all the investors who go for capital assets are assumed to be risk averse, and we will deal with this concept of risk aversion in more detail when you talk about utility theory. And this setup is for a one period model, and the expected utility of terminal wealth maximizers. So, this is the framework that all investors in the capital assets are assumed to be driven by three considerations. First of all, they are risk averse. Secondly, they are always looking at their portfolio strategies over a one period, or that is the holding period, and they are driven by the optimization requirements of maximizing the expected utility of the terminal wealth. So, basically you have terminal wealth and you calculate the utility of the terminal wealth, and this concept of utility will be introduced in subsequent classes. And then since the utility of the terminal wealth is a random variable, so you need to take into account what is the expectation of that, and since it is all driven by since these are investors of capital assets, so essentially they are going to be driven by efforts or a portfolio strategy to maximize the expected terminal wealth that is going to be available at the end of the holding period. Now, second assumption is that investors can make their investment decisions solely based on the mean and standard deviation of terminal wealth associated with the alternative portfolios. So, this means that amongst the different portfolios that are available for consideration, the primary driver has already been noted is the terminal wealth and maximization of expected utility. So, this decision of maximization of expected utility of the terminal wealth, the distinction between them or a preferential setup is driven from the point of view of the investors, with the underlying driver being the mean and variance. So, essentially the CAPM assumes that the entire exercise of maximizing in terms of the terminal wealth will be in the mean variance framework due to Markowitz. The third assumption is that the mean and standard deviation. So, since we have said that the mean and standard deviations will be the driver of the decision, so accordingly this mean and standard deviation of the terminal wealth, this exists, are finite and can be estimated, which is the reason why you can make an investment decision based on these estimations. The next point is all capital assets are divisible. That means, you can buy or sell a fraction of assets like stocks and bonds, and all the taxes and transaction costs are assumed to be non-existent, and please remember that this assumption of non-existence of taxes and transaction cost is in the context of the CAPM, the discussion of on CAPM. In reality, of course, they have to be taken into account, in which case the analysis becomes considerably more challenging. 5. There exists a single risk free interest rate, that means a single value of R subscript f introduced in the last class, and which is used for all borrowing and lending. 6. All assets including human capital are marketable. 7. The capital markets are perfect. So, this term perfect means the following. As the first thing it means is that all information is transparently available to everyone. That means, in all the investors have identical information, then there is no requirement for margin and C, there are no restrictions on either borrowing or lending or short selling. And finally, the last assumption is that all investors have homogeneous expectation in the paradigm of expected return. So, that means they calculate the expected return, variance and covariance in an identical manner over a single period investment window. All right. So, now that we have set up the framework for the discourse on CAPM, so we can now get into the equation that is driving that. So, accordingly, we will start by recalling the CML, the equation for CML that we have done in the previous class. So, recall that the CML or the capital market line was given by expectation of the return of portfolio is equal to risk free rate plus ERM, that is the expected return on the market portfolio divided by the standard deviation of the market portfolio into sigma p. Okay, now that we have recalled this, we can now focus our discussion on the CAPM. Now, what is the CAPM? The CAPM is a relationship wherein the expected rate of return of the ith asset is a linear function of the systematic risk of that asset given by beta I. So, here beta I essentially means that it is going to be the covariance of the return of the ith asset with the return of the market portfolio divided by the variance of the market portfolio. So, this is the same beta that we had determined in case of the linear regression, which we had done in our in one of our earlier lectures. So, accordingly, I will just first state the CAPM or the security market line, the equation for that, and then we will look at its derivation and some of the interpretation of that. So, accordingly, we have ERI, that is the expected return on the ith asset, is equal to RF plus ERM minus RF into beta I. Now, let me identify the terms here. So, here beta I is the beta of the ith asset. So, this will be given by sigma Im by sigma m square. Next, E of Ri, this is the expected a return of the ith asset. So, I have taken care of this term, RF as before is the risk free rate of return, and the remaining term, that is ERM minus RF, this is what is known as the market risk premium. So, this means that it is the additional amount of money that you make over the risk free rate RF as a result of your decision to go ahead and invest in the market portfolio as compared to the risk free asset. So, since this is an additional benefit or potentially a loss that you are going to get or incur as a result of taking up a risky position, that is the reason why it is known as the market risk premium. Okay. So, now once I have set up this equation, so let me now talk about the derivation of the CAPM. So, let us consider a portfolio P, and this portfolio comprises of an asset I with weight Wi and the market portfolio M with weight 1 minus Wi. So, this means the portfolio P has this asset AI and the market portfolio with the respective weights being Wi and 1 minus Wi. All right. So, what you can do is, so now we can make an observation here and make a note that the inclusion of asset I with weight Wi, what does that imply? So, this implies or is representative of the excess demand for asset I. And why I say that this is excess demand? That is because in equilibrium, that means in market equilibrium, the market portfolio is already inclusive of the asset I. So, ideally if we remember, the market portfolio is the point of tangency that we have on the efficient frontier. So, it is enough to actually consider the market portfolio as your investment, and obviously since the market portfolio includes all assets that are available in the market. So, obviously it also includes a certain amount of investment in the ith asset. Now, if instead of exclusively investing in the market portfolio, you have decided that you want to make also an investment in a particular asset, that means that in the new portfolio P, the amount of your investment in the ith asset is going to have a weight that is not just related to or in proportion to the weight of that asset in the market portfolio, but there will be also some additional amount of money in that particular asset. So, this means that amongst all the assets that are in the market portfolio, you have chosen to put in an additional amount of investment in just one asset, namely the ith asset, and this is because that there is an extra demand on your part to make an investment in the ith asset. Okay, so graphically this is going to look something like this. So, I look at the sigma p ERP plane, and this is RF, and this is going to be my point of tangency, which is the market portfolio M, and this is the capital market line, and I will take this curve to be EF to indicate that this is the efficient frontier. And what I do is that I will have this curve where I will indicate this asset I to be this point, and this is some portfolio M prime, which I will specify as I discuss the pattern of this curve I M prime. All right. So, now we can say that this portfolio P, which I have constructed with the ith asset in the market portfolio, will lie somewhere on the curve I M. Now, since the asset I is in M, remember that M is the market portfolio. So, it also always has to be inside that. So, the portfolio P contains varying amounts of money invested in asset I at various points on the curve I M prime, where M prime is the market portfolio excluding asset I. So, let me explain this. See, if you observe carefully at the CML, the line joining RF with M. So, when you have RF, this basically means that you are invested exclusively in the risk free asset, and this means that you are invested in the market portfolio. So, this line RF and M, in an analogous way, when I consider a portfolio P, then that portfolio is going to lie on this line. Now, if you are invested in the ith asset, then you are here. So, if you are invested in a combination of the ith asset and the market portfolio, then you are essentially lying on this line, and here on this curve, not the line but rather the curve, and here this M prime that you have. So, this I is an exclusive investment in the ith asset, and this M prime is a portfolio which is the same as the market portfolio, except that it does not include the ith asset. So, that means that if we take the market portfolio and remove the ith asset and proportionately increase or decrease the weights of the market portfolio, that will become the new portfolio M prime, which is almost identical to the market portfolio, except that it will not have the ith asset. All right. So, let us now look at a bit of an analysis of this curve I M prime. So, accordingly, we will look at what is the expected return and risk. So, therefore, we have ERP. What is this? This is going to be the weight WI into expected return of the ith asset, and the remaining weight 1 minus WY into expected return of the market portfolio. And accordingly, the sigma P square is going to be WI square sigma I square plus 1 minus WI square sigma M square plus twice WI into 1 minus WI into sigma I M, and this whole thing will be raised to half if I just take sigma P. So, now I have basically found out this relation sigma P E R P. Okay. Now, so accordingly, what I can say that as WI changes, remember that WI is the weight of asset I in portfolio P. So, as it changes, the corresponding changes in ERP as defined here and sigma P as defined here, these are, what are these going to be? This is going to be DERP divided by DWI, and this is going to be ERI minus ERM, and for sigma P, D sigma P DWI, this is going to be WI sigma I square minus 1 minus WI sigma M square plus 1 minus twice WI sigma I M. So, after some algebra, you get this expression divided by sigma P. So, now that we have the proportional change of the return and risk with respect to the ith asset. So, therefore, the change of ERP relative to sigma p, that means the slope of this in the sigma p ERP curve, this is given by so I will take d E of R p over d sigma p. This can be written as d E R p d W y with respect to d sigma p d W y, and this can be written as, so this will be E R I minus E R M from here, and this term will be in the denominator. So, the sigma p will come to the top and the denominator will have W I sigma I square minus 1 minus W I sigma m square plus 1 minus twice W I sigma I m. Now, the curve I m prime, so you recall that the curve I m prime that I have here, this will be represented by this ERP and sigma RP, and so accordingly this expression, that is the change of the expected return vis-a-vis the risk as given by the standard deviation, what is this going to represent? This is going to represent the slope of the curve I m prime. So, according to this, we can write that this expression here is the slope of I m prime. Now, in equilibrium, there is no extra demand for asset I. So, this means that there is no incentive for one to put in more amount of money in the ith asset as compared to the amount of money that is already invested in the ith asset as a part of being the market portfolio. So, this means that this is the scenario where that in a market equilibrium you will have the portfolio P comprising of exclusively of the market portfolio, that is the way W I is going to be equal to 0. So, accordingly, this is when, as I have just explained, W I is going to be 0. So, then this slope sigma p at W I is equal to 0, what is this going to be? This is going to be nothing but E R I minus E R M into sigma p, and I put W I equal to 0 in the denominator. So, accordingly, in the denominator I will get sigma m square. So, this will be minus sigma m square from this term here, and from here I will get sigma I m. Okay. Now, we make an observation that the slope of the curve I m prime when W I equal to 0. So, remember that this has to be reconciled with the fact that when W I equal to 0, then your portfolio P does not have any extra investment in the ith asset. So, it has the same investment as basically the market portfolio. So, reconciling that with the slope being evaluated at W I equal to 0, we can now make the following observation, and the observation is that the slope of the curve when W I equal to 0, this must be the slope of the capital market line, since the capital market line is tangent to the efficient frontier, which I have identified as E f at the point M. and also we recognize the fact that EF is tangent to Im prime at M. Okay, so now that we have made this reconciliation, so let us just recall what is the slope of the capital market line. So recall that the slope of the CML is ERM minus RF over sigma m. Okay, so I identified this slope at W equal to 0 as equation 1 and this slope as 2. So, this expression I will call as 1 and this expression I will call as 2. So, accordingly, since both the slopes have to be identical, so equating 1 and 2, by this I mean the expressions, what we will get? We will get ERM minus RF over sigma m. This is going to be ERI minus ERM sigma p divided by sigma Im minus sigma m square, which implies that ERM is equal to RF plus ERM minus RF over sigma m square into sigma Im. And this line, this is referred to as the CAPM or the security market line or SML. Now, I have actually put this CAPM when I began the discussion in a slightly different form. So, in order to obtain that form which involves the beta of the ith asset, we take into note the definition of beta. So, using the definition of beta I, which is the covariance of the asset with the market portfolio divided by the variance of the market of portfolio, we obtain from this relation we will get that E of, so this is actually ERI, please make this correction. So, we will get ERI is equal to RF plus ERM minus RF. So, this is the market premium into this term sigma Im over sigma m square. I will represent this with beta I, which is another form of for CAPM or the security market line. Okay. Now, I have used the term capital asset pricing model, and what I have done here is essentially I have instead got what is going to be the expected return on an asset in terms of the beta of that particular asset and the risk premium and the risk free asset RF. So, in order to justify this term that this has some relation with the pricing of an asset, what I am going to do now is I am going to talk about the scenario of and a qualitative discussion of how this is related to assets being priced correctly, and for that we will look at the scenarios of when the asset is overpriced and when the asset is underpriced in the context of the form of CAPM or SML given in terms of beta I, that is the last equation that we have obtained here. All right. So, we discuss now on over and under priced securities. So, accordingly, let us look at a simple example. So, let the current price of a stock be denoted by P0, and remember that CAPM is in a single period framework. So, accordingly, the estimated or expected end of the period price be given by E of P1. Remember, P1 is a random variable. So, you have to take the expected return. Then the expected, so this is actually the expected price which you call as estimate, and so the expected return is given by, so we will make use of the definition. So, what is expected return? Expected return E of R is going to be the expected price of P1 minus P0 over P0. So, this is E of P1 over P0 minus 1. Okay, now let us look at the over and under pricing aspect in the context of the CAPM. So, first of all, if P0 is low, now if P naught is small, then this quantity is going to be large. So, if this is low, then consequently E of R is going to be high, because E of R and P naught behaves in an inverse manner. So, once I say that this is high, this means that the E of R of the asset that you get will be greater than the expected return that is given from the formula for the expected return of the CAPM. So, this means that E of R is going to be greater than RF plus E RM minus RF into beta. Now, here I am dropping the subscript I for notational convenience. Now, let us look at the other case, that if P naught is high, that means this is large. So, this means that E of R is going to be small. So, then E of R is low, and this means that if it is low, that means E of R will be less than the expected return as given by, again, this expression given by CAPM. Okay. So, what does this mean graphically? So, graphically I can represent this as, so if I look at the expected return against beta, and this is my RF. So, this is a straight line. Remember that this is a straight line with intercept RF and slope with the variable beta as the x axis, and E of R as the y axis. So, this equation, this is what is known as the SML, with the slope being given by this. So, this means, so here I will have E of RM. So, this point here, so when E of R is E of RM, right. So, that means that in the relation E of R is equal to RF plus E RM minus RF into beta. So, when E of RM is the expected return is E of RM, this becomes E of RM. So, E of RM minus RF will be equal to E of RM minus RF into beta. So, this means that beta is going to be equal to 1. Okay, so that is a side issue. Now, coming back to the SML. So, what happens here is that if your E of R is greater than this value which is given by the security market line. So, this means that if it is higher then that it lies above the security market line. So, this expression means that the expected return lies above the security market line. That means that the price is low and the price has to increase, and the market will correct itself to increase it. Likewise, when I have E of R is less than RF, then this means that the price P naught is too high, and then it needs to come down in order to attain the market equilibrium given by CAPM. So, these two statements that I have just now made, then I am going to reconcile them and conclude the following, that if you are above the SML, then this means that, so this is the scenario, that means that the asset is or the security is underpriced, and if you are below the SML, then this means that what you have is an overpriced security. Okay, so we now come to the last topic of this lecture, that is the single index model, and the reason I am introducing the single index model is that we can better appreciate the interpretation of the term beta I, and secondly to introduce the concept of how the risk of a particular asset or a portfolio can be decomposed into two different kinds of risk, namely the systematic risk and the non-systematic risk. So, accordingly, we start the single index model. So, we consider this to be a time dependent model, that means the return at of an asset I at time t, that means between the in time t minus 1 and t. This will be given by some alpha I into beta I r m t plus epsilon I t. Now, it is called a single index model because the return of the asset at time t is going to be modeled as a function of the return on the market at time t, which is equivalent to a market index. So, here the single index refers to the market index whose return will be denoted by RMT, and remember that this is a random variable. So, here what we have is that alpha and beta I, these are the intercept and slope, and these are determined as a result of regressing the rate of return from asset I. So, that means RIT in period t, that means from the time point t minus 1 to t, with the concurrent rate of return from some market index, which I will denote as RMT in period t. So, what it means is that I consider different time intervals as 0 to 1, 1 to 2 and so on, and I look at what is the what are going to be the return in those time intervals or those single periods, and then I will denote the period t to be an investment that was done at time t minus 1 and held up to time t. So, accordingly, the corresponding return for the ith asset is going to be denoted by RIT, and that of the market is going to be denoted by RMT. So, what I am going to do is I am trying to look at, so what I will do is that I will treat my Ri to be some random variable y, and I will treat Rm to be some random variable x. So, this is similar. So, I will treat my Rit to be some y and Rmt to be random variable x, and you want to find a linear relation between them. So, this will be something like y is equal to alpha plus beta x plus epsilon, and remember that this epsilon is going to be nothing but y minus alpha plus beta x, a form that we had seen when we were looking at linear regression. So, this is the point where I had mentioned also at that time that we are going to see an application of the linear regression. Okay, so, here remember this alpha plus beta x will give a linear approximation to the return on the asset I, and then the difference between the actual value y, the actual return RIT, and the one that is basically given by this linear regression form of alpha plus beta into x, that is going to be the error. So, accordingly, I come back now to this discussion on RIT and RMT. RIT and RMT, recall that these are the returns of the asset and the market, and I am going to correlate them through a linear relation, and here we will make use of the linear regression approach results that we have already derived. Alright, so now in order to carry out this exercise, I need to make certain assumptions, and these assumptions are following: that the expected value of epsilon it, which is the residual factor. So, remember that here I will take epsilon it is the residual error for this is the residual error term for asset I in period t. So, the assumption, first assumption is the expected value of this is going to be 0. The second assumption, or rather an introduction of notation, is that I will denote the variance of epsilon it with the notation sigma square epsilon I. Thirdly, I will assume that the covariance of epsilon it and rmt is going to be 0. That means, epsilon it and rmt are uncorrelated. The next thing I will do is that I will take that covariance of epsilon it and epsilon is equal to 0 for t not equal to s. That means, they are serially uncorrelated, that means, they are sort of time independent. And the last property that we can make use of or state is covariance of epsilon it and epsilon jt, that means, the residual error that will be 0, that is, they are uncorrelated. Okay. Now, this RIT, so coming back to the relation RIT is equal to alpha I plus beta I RMT plus epsilon IT. Let us calculate the expectation, variance and covariance of all this. So, the expectation here, so expected value of RIT, of course, given RMT, this is going to be simply the expected value of alpha I, which is alpha I, plus expected value of beta I RMT, which is beta I, into RMT. Remember that I am taking conditional expectation, so this is fixed, plus 0. And if I just take the expected value of RIT, of course, I will have to write this as alpha I plus beta I plus expected value of RMT. And this expected value is 0 by my first assumption. Alright, so now next let us come back to this the second moment. So, variance of RIT, what is this going to be? Let us replace RIT with this expression. So, this is going to be variance of alpha I plus beta I RMT plus epsilon IT. What is this going to be? This is going to be the expected value of alpha I plus beta I RMT plus epsilon it minus the expected value of alpha I plus beta I RMT plus epsilon it whole square. Now, here this alpha I and this expected value of alpha I will cancel out. This beta I RMT will combine to give me the expected value of beta I into RMT minus ERMT. And here this is just going to be epsilon it minus this term, this expectation is going to be 0. So, this square is going to give me beta I square into expected value of RMT minus ERMT whole square plus expected value of epsilon it square. Now, this can be written as expected value of epsilon it, which is 0 square, plus I will have a term which involves covariance of RMT and epsilon it, and that is going to be equal to 0. So, this becomes then beta I square is equal to into sigma m square plus sigma square epsilon I, and this term is what is known as the systematic risk, and this is known as the unsystematic risk. So, we can see that this variance of the asset can be decomposed into systematic risk and unsystematic risk. The unsystematic risk here means that it is that component of the overall risk that is happening as a result of the behavioral pattern of just the asset I, and remember that this only has the subscript I, and the systematic risk which comprises of the term beta I square sigma m square. Recall that here sigma m square is the market term, and also by definition beta I reflects the behavior of the asset I vis-a-vis the market the market return. So, accordingly that component which is the systematic risk is called systematic because it is related to the overall global behavior of the market. And very often the unsystematic or the non-systematic risk, since it is something that is attributed exclusively to the asset, it is what is known as a diversifiable risk. That means it can be reduced by choosing a diversified portfolio. However, the term sigma m square beta I square for systematic risk, no amount of diversification can actually get rid of that, because it is something that is a consequence of the overall behavior of the market. Alright, so we come now to the last derivation, that is covariance of RIT and RJT, and this is going to be by definition expected value of RIT minus E of RIT into RJT minus E of RJT, and this can be written as E of alpha I plus beta I plus epsilon IT minus expected value of alpha I plus beta I plus epsilon IT. There is actually an RMT here, an RMT, and this term multiplied by alpha j plus beta j RMT plus epsilon JT minus expected value of alpha j plus beta j plus epsilon j t, and beta j also has the RMT term. So, if you cross multiply, this becomes expected value of beta I RMT minus E of RMT plus epsilon IT multiplied by beta j RMT minus E RMT plus epsilon JT, and this will simply become beta I beta j sigma m square. So, the previous case, so that means that this can be written as sigma I square. So, the variance, just to recap, sigma I square is beta I square sigma m square plus sigma square epsilon I, and the covariance can be written as sigma I j is equal to beta I beta j sigma m square. Alright, so this concludes this lecture. Just to do a recap of what we have done in this lecture, we essentially looked at an extension of the capital market line and introduced the very important concept of capital asset pricing model, and we derived the relation for the capital asset pricing model, and we also gave an interpretation of the capital asset pricing model in the context of determination of whether the asset is overpriced and underpriced, and how it relates to the security market line or CAPM. And finally, we talked about what is the single index model and looked at its expectation, variance and covariance. Thank you for watching.